Today we are going to be talking about something called the next generation method, next generation matrix. This is continuing our discussion of adaptive dynamics and how we can use adaptive dynamics to model phenotypic evolution. So last week, we were talking about the distinction between evolutionary stability and convergent stability. And just a reminder here, you can think of your while these are not completely independent of each other, we can have, for example, a singular strategy that is convergent stable but not evolutionary stable, or vice versa. Or they could have both be convergence and evolutionary stable, or neither convergence nor evolutionary stable. You can think of these as being a little bit like evolutionary stability is telling you about the curvature of your invasion fitness at a singular strategy. So you can think of your singular strategy as a potential evolutionary endpoint. That's a point where your selection gradient is equal to 0. So at that moment, instantaneously, there is no change in your trait values, your phenotype. However, we then need to look at our second order derivatives to see what's actually happening. This is analogous to what we do in just standard dynamical systems, right? We need to look at our higher order derivatives sometimes to figure out what's going on. And your evolutionary stability is a bit essentially like being the top of a mountain. So a fitness peak, you can't get higher than that locally. If a mutant is nearby to that mountaintop, it has a lower fitness value, therefore it is uninvadable. The fitness peak is uninvadable, so that's evolutionarily stable. Whereas if it's like a valley, it's a fitness minimum, then nearby mutants have higher fitness, so they can invade. And then convergent stability is all about whether you can reach that point, whether you can reach that singular strategy. So I like to say that something that is evolutionarily stable, but is not convergent stable, is like the top of a mountain where there's no path that leads you to the top of the mountain. So you can't get there through small steps. You could make one big jump, you could helicopter in. That would be like having a large mutation. So it is, in some sense, obtainable through those large mutations, but through this gradual process of small mutation and replacement, there's no path that leads you to the top of that mountain. That's our Garden of Eden. And then the one that's really confusing, I guess, is the one that is evolutionarily unstable. So it's like a fitness valley, but is convergent stable. And this is where we have a branching point. And this is something that kind of looks like a mountaintop from afar, but because as you move through this phenotypic space, there's a feedback between invasion fitness and the environment. So the current phenotype creates the environment that the mutant invades into. Okay, you can think of this, maybe an example that's a little bit more concrete is something like an infectious disease. It will essentially set up the profile of potential hosts for other pathogens that can invade. Okay, so it will affect the level of immunity and the type of immunity in the population. It will affect potentially the number of hosts that are available. So any new pathogen that comes in has to invade in that given environment. So when we have a branching point, what's really going on here is we are converging towards this thing that looks like a fitness maximum, but as we're moving through this space, it's a bit like a trampoline. It deforms, it changes. Okay, so once you get there, it's no longer a fitness maximum, it's actually a fitness minimum. That was a little bit weird. We're going to come back to that in the future. We talked a little bit about pairwise invasion plots as well, where we look at our resident traits versus our mutant traits, and then we just see, okay, this is our invasion fitness. It's just a 2D function. So you can think of this as being a surface, but we just look down on top of the surface, and that tells us something graphically about what is going on to our traits. So it tells us where our singular strategies are, and also by looking at the geometry of that surface, you can see about whether it's a singular strategy is convergent stable or evolutionary stable, and therefore conclude what type of evolutionary dynamics you're going to see. Okay, so one of the key things so far is that we have only considered scenarios where we can write down one equation, say for our mutant invasion dynamics, and then from that immediately write down what our invasion fitness is. And that works essentially when our populations are unstructured. The key thing really is that the growth rate of our mutant only depends on a single ODE. Okay, so they might have in theory, you could have multiple ODEs, but only one of them affects mutant growth. Okay, but there are many cases where populations will be structured. And we're going to go through an example of this today. And we have to now use a method called the next generation method to now derive an expression that is a proxy for invasion fitness. Okay, so it's a little bit more involved in these structured examples. So that's what we're going to go through today. We're going to go through these structured models and how we find invasion fitness in them. We need to learn a little bit of linear algebra along the way. We're not going to go too deep into the reasons behind this because it's kind of beyond the scope of the course. We'll talk about the next generation theorem. And to understand that, we need to know what the spectral bound and spectral radius of a matrix is. And then we'll find this invasion fitness proxy at the end. Okay, so to start off with, just because we'll be coming back to this at a few points today, or building on this, this was our model of intraspecific competition that we've met a few times now. So just remember, this is the rate of change for a population with phenotype xi. So ni is the number of individuals or population density of phenotype xi. Has an intrinsic growth rate of r, which is positive. And then it has this competition term here in the middle, this 1 minus aij term, or sum of aij times by nj, is basically saying what is the competitive impact of an individual with phenotype xj on an individual with phenotype xi. And then we've got a carrying capacity for phenotype xi here. Okay, so we've looked at this already, and we've seen a few examples about when we can get, say, continuously stable strategies from the system. But the first stage to any of the adaptive dynamics we've done with this is to first of all write down invasion fitness. And in these models, we've been able to write this down as Wxm of xr. So this is saying what is the invasion fitness of phenotype xm, our rare mutant, into an environment that is defined by our resident with phenotype xr. And this was just, in these simple models, the per capita growth rate of our mutant at our residence equilibrium. Okay. So actually there's a pre-stage to this. Remember, we actually need to find what this equilibrium is here and check that it is locally asymptotically stable. I'm skipping over those steps here just because we've already done that a few times. But in terms of finding invasion fitness, this is pretty simple to write down, okay? We've got an equation up here for any phenotype. And then I'm just going to say, okay, well, what happens if we start off with one resident phenotype at its equilibrium and then introduce a rare mutant? So I've added a second equation now. So we'd have a DNR dt and a DNM dt. And that DNM dt is evaluated at our residence equilibrium. Okay, we can do this because the population is unstructured. In other words, the mutants' reproduction, or new mutants, are only produced by a single ODE. This is also referred to as the invasion exponent sometimes. Basically just telling us, can our mutant invade? Remember, this all as well came from thinking about perturbations away from our resonance equilibrium and analyzing the stability of that resonance equilibrium. If this quantity is positive, then we're going to move away from that resonance equilibrium. In other words, our mutant can invade. Okay. Let's think about a slightly different variation on this idea. So what happens now if our population is split into young and old individuals, or young and adults? I'll also sometimes refer to the young as juveniles. Okay. So suppose now dyi dt is going to be the population density of young individuals with phenotype I. And I'm going to say that this is R times by AI. That's by 1 minus sum over all phenotypes. That's by with aij, so little aij, which is the strength of competition, just like we had in the previous model. We're just going to sum over our adult class here. We're going to assume essentially that adults are the only individuals who are consuming sufficient resources. We have our carrying capacity that we had before. Now, in this sense, the carrying capacity kind of breaks down a little bit, but we're going to keep the idea of the same notation here. Essentially, it's just a parameter or a function of our phenotype that is controlling the strength of density dependence here. Okay, and the strength of density dependence on births. Okay, so at the moment, this looks a bit like what we had before, except now we've got these age-structured compartments. We're going to subtract from this minus g plus d times by y. And then we're going to have a separate equation for our adults, phenotype XI. Yeah, there should be a YI there. That's going to be G times by YI minus D times by AI. Okay, can anyone tell me, so we've introduced two new parameters here, G and D. Can anyone tell me what they think D and G correspond to? Yeah.
G is like the young people growing old.
Yeah, so
Is that right?
exactly, yeah. So you can think of this as a maturation rate, G, and D is a per capita death rate. In fact, I'm going to put bounds on these as well. Typically, I do often miss these out because we're talking about positive parameters unless otherwise specified, but just to make sure it's clear, these are the bounds for these parameters. So we've got a per capita death rate. We're assuming here that our young and old individuals have the same per capita death rate, for example. We're assuming that there's this maturation rate, so individuals move from this class into this class of rate G. This also means that 1 over G is the average juvenile period, because these are exponentially distributed rates. And other than that, it's basically the same. I mean, one of the key things here is that we're assuming that young individuals don't reproduce. Okay, so only adults are able to reproduce here. So these are reproductively immature individuals and only adults reproduce. I'm also going to define here Aij is equal to, in this case, I'll call it e to the xj minus xi, and ki is equal to k hat e to the minus xi squared for some k hat greater than 0. We've met these functions before as competition functions, Aij, and some function describing how the phenotype affects the carrying capacity for a population composed entirely of that phenotype. Okay, let's do a quick bit of analysis on this system before we delve into adaptive dynamics. Typically in class, I'm not going to go through this first stage in detail when I go through these examples, just because it can be a little bit laborious to show every single time this is an ecological equilibrium, how have we derived it, and so on. I'm kind of expecting you guys to be able to understand how to derive equilibria for this, if you're not familiar. With this, I mean, we went through this essentially in the linear stability analysis review lecture. I also have my videos for Math 360, which also go through finding equilibria in, say, 2D systems or any system of nonlinear ODEs. So if you're unfamiliar with those, you can find those on my YouTube channel if you need a bit of additional revision on that, okay? So often I'll do something like this and I'll just kind of jump to this last stage here and say that it can be shown that there is a non-trivial equilibrium here. Y star is equal to D A star over G, and A star is equal to Ki by G times by brackets R minus D squared over AI times by RG. Hopefully I've got that right. And this is biologically realistic for G times by R minus D squared or greater than 0. Okay. Like I said, I've not shown the derivation for this. All I've done is I've set these equations here equal to 0 when there's just one phenotype in the population. This AI here really should be AII, actually. It's phenotype I. But seeing as there's only one phenotype in the population, this is just a constant. Can anyone tell me where this condition here comes from? Why have I put this condition here?
We need A star to be positive.
Yeah, so I've said that this is a non-trivial equilibrium. So when I say non-trivial, I mean, so non-trivial up here. I mean that both of our populations are non-zero. Okay, so we need this term here, which appears up here in the numerator of A star to be positive for both Y star and A star to be positive. Okay, so that's our non-trivial equilibrium. There is also a trivial equilibrium, but we don't care about that because if the population is extinct, that's what I mean by trivial equilibrium here. If the population is extinct, no evolution is going to happen. So we're only going to focus on cases where evolution is possible. Okay, so we need to check that it is locally asymptotically stable. We can find our Jacobian matrix. This is going to be minus D minus G, minus 1 over G times by G, R minus 2D minus 2D squared. I hope that's correct. G and minus D. Okay, so we've got a Jacobian matrix. We can use the Routh-Hurwitz criteria here. If we note that the trace of this matrix, I'll call this J star. So this is just to make sure it's clear. This is our Jacobian matrix when it's evaluated at the non-trivial equilibrium. It has trace minus 2D minus G, which is negative. The determinant's a little bit more complicated, but not too bad. The determinant, we're going to have minus D times by minus D minus G. So we're going to get D times by D plus G. The negatives will cancel out. And then we're going to have minus this times by this. So again, we'll have a plus. The G's will cancel. And we end up with a G times by R minus 2D minus 2D squared. And then from here, we can see that we're going to have a D squared here, which will cancel with one of those D squareds at the end. We're going to have a plus DG and a minus 2DG. So we'll get rid of that 2 as well, which just gives us G times by R minus B minus D squared. So remember, for our Routh-Hurwitz criteria, for our matrix to have negative real parts for our eigenvalues, trace has to be negative and the determinant has to be positive. So the non-trivial equilibrium is going to be locally asymptotically stable. It's going to have negative real parts to its eigenvalues if G times by R minus D is greater than D squared, which, if you'll note, this condition here is the same as this condition here. Okay, so that basically means when it exists, when the non-trivial equilibrium exists, it is locally asymptotically stable. So that tells me that before I introduce a rare mutant, my population is going to tend towards this equilibrium here. Any questions so far? Okay, so that's all the ecological analysis. So whenever I'm talking about doing, ecological analysis, I'm basically talking all of these stages up to here, analyzing the residence equilibria, finding out when they're locally asymptotically stable, or at least when the non-trivial one in this case is locally asymptotically stable. So the next thing we need to do is write down our invasion dynamics. So now we've got 2 equations for our rare mutant. So now we're going to have dym dt is equal to R times by A sub n times by 1 minus, well, here we're going to have just a mutant that is rare invading into a resident population at its equilibrium. Because the mutant is rare, we're assuming the mutant essentially never interacts with other mutants. Okay, so that means that rather than that sum over our resident type and our mutant type, we just need to look at interactions between our mutant and our resident population, which is at population density A star. And we've got our carrying capacity for our mutant, Km. And then we've got minus G plus D times by Ym. And then our equation for our adult mutants, which is G times by Ym minus D times by Am. So previously at this stage, in our unstructured populations, we only had one equation. So we could just divide through by the population size of our rare mutant to get its per capita growth rate when it was rare. And that was in our invasion fitness. We can't do that anymore because the population is structured. Okay. So we need to take into account the contribution, or essentially in this model, how long individuals spend in this juvenile stage, how long they spend in the adult stage on average, and what is their contribution for this adult stage into the growth rate here. Yes.
So by structure, you just mean that if there's a young and adult stage phase.
Yeah, whenever in any sort of model where there is more than one ODE that describes the growth of our mutant, then you end up in this situation. If I make a quick adjustment to this, just to demonstrate a case where it wouldn't matter. Suppose we still had two equations for our system, but suppose, just for argument's sake here, this was a model where only the young, say, only the young individuals reproduce, and the older individuals don't reproduce. We'd have something that looks like this. In this case here, you would actually be able to ignore this equation, because even though it's structured, the growth of our mutant here only depends on Ym now. Okay, so the AM is kind of like a dead end. There's no feedback from this class into this class now with these changes that I've made here. So the structure itself is important insofar only as it affects the reproduction of our mutant. This is a structured model where here the older individuals have no effect on the growth if they have no kind of new individuals being produced based on the density of this class. Therefore, they don't matter. Yes.
So like AM doesn't show up in that.
Exactly, yeah. So in that case, we would just be able to divide through by by Ym, and we would have our invasion fitness based on that. However, if I just go back to our what we had before, because our adults feature in this equation here, we have to take into account the density of adult mutants. Okay, so now what do we need to do? Well, if we think about, again, just going back to basics, what we're trying to do here, we've got a resident population at its equilibrium. We're introducing a rare mutant. So now we started off with two equations, but now we've got four ODEs. And we want to essentially analyze the stability of that resonance equilibrium. We did this before when there was just one equation for the resident and one for the mutant. Now we're doing for two equations for the resident, two for the mutant. But essentially what we're doing is the same thing. We're just seeing whether a small perturbation away from that, which is our mutant, whether it can invade, and therefore is that resonant equilibrium stable. So we need to look at our Jacobian for our resident mutant system. So this is a 4x4 Jacobian. I'm not going to write this all out, but it's our partial derivatives of each of our equations. So we're going to have partial with respect to y, a, ym, am, and then it's going to be dy dt, dA dt, dym dt, and dy am, sorry, dam dt at the end. Okay, so I'll just write out the first row just to make that clear. So taking our partials with respect to our residents, and then with respect to our mutants of each equation. Bring partials in here. Should just be normal. And then we'll do this for each of our equations. So d by dy of dA dt. Again. Similar. And then we go through d by dy of dym dt. And then d by dy of dAm dt. So it's just a 4x4 Jacobian. The key thing to note now is that we can write this in a block form. Okay, we can think about splitting this according to whether we are taking derivatives with respect to our mutants or with respect to our residents, and whether we're talking about our resident equations or our mutant equations, right? So we can write this in block form. We can write this as, I'll call it J res. This is our resident submatrix, our Jacobian that we had before. Okay, so if we just have the resident by itself, this is what you get, a Jacobian of that 2x2 system. In this bottom right-hand corner, we've got dym dt, taking the partial of that with respect to dym, respect to the AM, and then so on for our second equation for our adult mutant. Okay, so this is our Jacobian if we just had our mutant there. Or rather, it's our Jacobian. How are our equations for our mutant dynamics changing with respect to the mutant population densities? Okay, and then what else have we got? Well, our top right corner is going to be how are our resident populations changing with respect to our mutant. So these is just going to be 0. And then we're going to have some matrix S, which I'm not going to bother talking about. So we can write this in block form where each of these matrices here are just the ones correspondingly above. So this is in block form. Okay, so we want the eigenvalues again. Yes.
Sorry, that 0 is just a 0 matrix. Right?
Yes, that's a 0 matrix, yeah. So it's a 2x2 0 matrix. So to find the eigenvalues of J, we need to consider our characteristic polynomial. So we need to set this equal to 0. So we have determinant of J minus lambda I, where lambda are our eigenvalues, which is just the determinant of this block matrix minus lambda times by I. So J res minus lambda times by I. I mean, there are two I's here. This I here is a 4x4 identity matrix, and this is a 2x2 identity matrix. Hopefully that is clear. We have an S matrix, a 0 matrix, and then mutant Jacobian minus lambda times by I. I'm going to just put an I4 here and an I2 here just to make sure it's clear. These are different sized identity matrices. Okay, now because this is in block triangular form, the upper right block, it is written down the other way originally. The upper right block is a matrix of zeros, so 2x2 matrices of zeros. So the determinant can be calculated as the product of our diagonal blocks. So the determinant of J minus lambda I is just going to be the determinant of J res minus lambda I times by the determinant of J mut minus lambda I. This is just linear algebra. Nothing new here, but just a recap of where this comes from. So all this is doing is it's telling us that the eigenvalues of our matrix J, our big Jacobian, our 4x4, are the union of the eigenvalues of these two matrices. Our submatrices J res and J mut. Okay, so because we already know that our eigenvalues of our our resident Jacobian all have negative real part. We know this because our non-trivial resident equilibrium is locally asymptotically stable. In other words, if I go all the way back up to here, this essentially is our J res. Yeah, this is what we started with. And we've already shown through the Routh-Hurwitz criteria here that it is locally asymptotically stable when it's biologically realistic. We're going to assume that it's biologically realistic because otherwise we're in a trivial case. So we know that the eigenvalues here are going to be negative. They're going to have negative real part at least. So that means that we only need to consider the eigenvalues of J mut to determine if the mutant can invade. And this is just like we did in our invasion dynamics before, when there was just one equation. Okay, now we've just generalized it to there being as many equations as we want there to be. Okay, we'll always end up in this situation where we have this block form for our Jacobian, when we have our resonant and our mutant dynamics, which means we can always just focus on finding the eigenvalues for our mutant Jacobian. That will tell us whether our mutant can invade. Okay, so we just need to look at our mutant Jacobian, and for our model that we've got here, we're going to have minus d minus g, r times by 1 minus AMR A star over KM, G and minus D. So this matrix here, this Jacobian, just comes from looking at the partials of these mutant dynamics here, okay, with respect to YM, with respect to AM. Okay. Is everyone keeping up? Is the pace okay, or do you want me to slow down? Slow down a little bit? Okay. Do you need me to recap over anything?
Most of it's fine.
Yeah, okay, just, sorry, yeah.
Could you recap over the part why we're only concerned with looking at J mut and not J res?
Of course, no problem. So because we can write so just to recap a little bit more, what we're doing, if you remember, is we've got our resident system at its equilibrium. This matrix up here has is locally asymptotically, sorry, our resonant equilibrium is locally asymptotically stable. So therefore, this submatrix up here, J res, has negative real parts for its eigenvalues. Okay. Now, because we can then write this Jacobian for our resident mutant system in this block form, where one of these matrices up here is just zeros, that means just through some linear algebra, our eigenvalues for our resident mutant system, evaluated at our resonance equilibrium, is going to be the product of the eigenvalues of this submatrix, or sorry, the union of the eigenvalues of this submatrix and this submatrix down here. Okay, so we already know that these eigenvalues have negative real part. We want for our mutant to be able to invade this equilibrium to be unstable. So in other words, we need to find the leading eigenvalue of this matrix down here and see when is that positive. If that's positive, then that means our mutant can invade. Therefore, our resident mutant system here, evaluated at our resonance equilibrium, is not going to be stable. So our mutant is going to be able to spread into the system. Does that make sense?
Yeah.
Yeah. Was there anything you wanted me to recap?
No, that's good.
Okay. Please, anytime you guys want me to recap anything, or if I'm going too fast, please just let me know. Generally, if I don't see any feedback from people or confused faces, I assume that things are okay. Maybe that is the wrong assumption to make, but please feel free to interrupt. Okay, so we can write down our Jacobian, our 2x2 Jacobian for our mutant dynamics. It looks very similar to our Jacobian that we had for our resident population. One of the key differences will be in this term up here. We've got this A star here, and there was no, there was no AM on the outside. Sorry, there was no A on the outside, or there was no A star on the outside. So this term up here differs. We go back to our Jacobian that we had before. It's already had the A star subbed in, but it's slightly different. Okay, so just make sure that you don't just write down the same Jacobian again. It's ever so slightly different now because we're only accounting for interactions between mutants and residents, no interactions between mutants and mutants. Okay. Okay. So at this stage, because we're essentially just doing linear stability analysis, we've got a 2x2 matrix here. We can find the eigenvalues for this matrix. It's not sufficient just to look at the Routh-Hurwitz conditions because we actually want to find invasion fitness. That means we need to find the largest eigenvalue of this. Okay, so finding eigenvalues of a 2x2, not the best, not the worst, right? In general, if you get into much larger systems, suppose this was now a 4x4 matrix of our mutant dynamics, that's going to be pretty nasty to do. But even in these 2x2 cases, it can be a little bit laborious. So one thing we can do is we can essentially translate this problem using something called the next generation method. This next generation method is still an eigenvalue problem, but we shift it in a way that uses some biologically relevant assumptions about how we ultimately we're going to decompose this matrix. This gives us a new matrix, which is called the next generation matrix. And typically, because of the biologically realistic assumptions we make when we do this kind of fancy transformation, we end up with lots of zeros in this matrix, which means that often we can just read off our eigenvalues straight away. So that's it's a cool little trick, which helps you find the invasion fitness without having to actually go through the process of solving the characteristic polynomial. Okay, I'll go a little bit longer and then we'll have a break in 5 or 10 minutes, okay? So before we can get to the next generation matrix, we just need to go through a couple of bits of terminology. They're pretty straightforward and we won't spend a lot of time with them, but it's just to understand where this next generation method kind of comes from, or at least what it says. The first thing is we need to define the spectral bound, or S of M, where M is a matrix, is any matrix. And this spectral bound is just the maximum real part of all eigenvalues. Okay, so you take all your eigenvalues and you find the maximum real part from those eigenvalues. That's called our spectral bound. So what we really want is for our mutant to be able to invade, we want the spectral bound of this matrix to be positive. So the spectral bound of J mut has to be positive for our mutant to invade. This is basically just saying the largest real part of any of the eigenvalues from this matrix has to be positive. So remember, we only need one of the eigenvalues, at least one of the eigenvalues of this matrix here to be positive for our resident mutant system evaluated at our residence equilibrium to be unstable. In other words, for our mutant to be able to invade. Okay? Okay, so that's the first bit. The second bit is we define something called the spectral radius, or rho of M. And this is just the maximum absolute value, or modulus, of all of our eigenvalues. So close to our spectral bound, but now we just take the absolute value or the modulus of all of our eigenvalues, we find the maximum of those. Okay. These are just definitions from linear algebra. And we're not going to go into the details, like I said, of where the following theorem comes from, because that's not really the purpose of this course. We're just going to use this result. There is something called the next generation theorem, or NGT. Sometimes I'll just refer to it as NGT. And this tells us that for any non-singular matrix A if we're able to write this matrix in the following form, A is equal to F minus V, where our F and V satisfy certain criteria, then it's going to tell us something about the relationship between the spectral bound of one matrix and the spectral radius of another matrix. That might seem at this stage very abstract, but ultimately, if you remember, the point of doing this is we're trying to find the largest eigenvalue of this matrix here, because that gives us our invasion fitness. So that's telling us something about we want the spectral bound to be positive for our mutant to be able to invade. We can do a clever transformation. Okay, so what is this decomposition? We write it in the form A is equal to F minus V. We'll talk a little bit about what these F and V matrices actually are in a moment. These matrices have to satisfy a few criteria, though. One of them is that our F matrix has to have all of its elements non-negative. The second is that the spectral bound of minus V has to be negative. In other words, all of our eigenvalues have to have negative real part for our matrix minus V. And then if we take the inverse of V, all of the elements in the inverse of V have to be positive. Yeah, I'm not going to go into the details about where these conditions come from and why we need these conditions, because that is beyond the scope of this course. Okay, so you're not going to be able to expected to remember those conditions. Yes.
Sorry, what is the second one again?
This one here is the spectral bound of our matrix minus V has to be negative, which is just saying that all of our eigenvalues have to have negative real part, because the maximum has negative real part. They all must have negative real part. Yeah. So in principle, whenever we do this decomposition, we should make these checks. Was that a question or a stretch? The last one as well. This is saying that all elements of our inverse matrix V, inverse of V, have to be non-negative. So just copy this here. All elements in our inverse matrix V are non-negative. Okay, you're probably thinking, why are we doing this? Well, if you make this decomposition in this way, it ensures that the spectral bound of matrix A, if that is negative if and only if our spectral radius of the matrix F times by V inverse is less than 1. If our spectral bound of A is positive, this occurs if and only if the spectral radius of this matrix F times by V inverse is greater than 1. And the spectral bound of A is equal to 0 if and only if the spectral radius of F of V inverse is equal to 1. Okay. Again, it seems at this point like we're just making the problem more complicated. But the key thing is that this is just shifting the eigenvalue problem, right? The key thing is finding the eigenvalues of this matrix A might be difficult. Typically, finding the eigenvalues of this matrix here is way, way easier. Yes.
So theoretically, all the adaptive dynamic stuff we've done, could we have applied next generation method, or?
In a sense, well, I mean, we always all the stuff that we've done so far has only been unstructured equations. So you've always just been able to write down your invasion fitness. There's no matrix to write down. But in all of there's no need to do this, but because you have no matrix there to convert. Could you write it down? I guess. Yeah, you wouldn't really be able to. I'm not sure there's as a direct analog, because we're essentially just able to jump straight to the eigenvalues effectively of just a 1-by-1 matrix is kind of what you're doing. A good question. Okay. Yes.
Why is it called next generation theorem?
That's very good. We will hopefully. Let's see if I've actually written it down in my notes. I think this will probably be a good time for a break anyway. I think I come back to this towards the end, possibly. But the headline is that this is called the next generation matrix because it's telling you what the contribution from each of your current classes is going to be in the next generation or the next kind of moment in time. So this next generation is about when you decompose this matrix in a biologically realistic way, it's kind of telling you the contribution of each class to the future of each of those classes. So that's why it's called this next generation matrix. The next generation kind of breaks down a bit if we're talking in continuous time. You could apply the same methods in discrete time, in which case that is a one generation to the next. Okay. Okay, let me just do this slide and then just because then we can go to an example straight afterwards. So this matrix F V inverse is our next generation matrix. Okay, so whenever you hear next generation matrix, it's just the product of F with V inverse. Hope you remember how to do matrix multiplication. And this set of conditions at the bottom, or this outcome at the bottom, is basically just saying that our spectral bound, in other words, our maximum real part for the eigenvalues of our matrix A, is sign equivalent, so it has the same sign as the spectral radius of this next generation matrix -1. All that we're doing here is we're kind of shifting things around. So since we only care ultimately about the sign of invasion fitness rather than its magnitude, we have transformed things. They're not going to have the same magnitudes, right? But they will have the same signs, and that's the key thing. So all we need to do then is to find the sign of this spectral radius of our next generation matrix -1, and that will tell us what the mutant conveyed. Because we only care about signs, we don't care about the magnitudes. We can make this transformation. And typically, it's much, much easier to find our eigenvalues of this matrix than it is to find them of this matrix. Yes?
Don't F and V have to be squared?
They will be because, yes.
Yeah.
I should say up here. I'm thinking of this in terms of our Jacobians, which are always going to be square.
Right.
So this should be a non-singular square matrix. Yes, thank you. For the general theorem, yes, they have to be square.
Right.
So like I said, at first it might seem that there's no advantage. We're making things more complicated. We're having to find an inverse of a matrix and all of that jazz. But this is typically gets more and more powerful the more equations that you have to deal with. Because like I said, suppose your mutant dynamics, suppose you had 4 stages. Now you've got to find the eigenvalues of a 4x4 matrix. Typically, when you do this translation, you might be able to just read off the matrix, the eigenvalues straight away from your next generation matrix. Okay, so it grows in power the more classes that you have, but it's still usually quite handy to do, and it also tells you something biologically realistic, which I'll come back to later, about each of the terms within that matrix. Okay, so like I say, so choosing a sensible, and by sensible I mean essentially biologically meaningful decomposition. So when I say decomposition, I mean this decomposition up here. So a sensible decomposition usually ensures that all of the conditions for requiring the next generation theorem to be used are actually applied. You kind of don't have to make those checks essentially, because if you do things in a sensible way, they automatically are satisfied. And it usually results in this triangular next generation. Okay, so we'll go through an example. Let's have a break for about 10 minutes, and then we'll apply this to our structured competition model and see what happens. Okay. Okay, I'll start up again. So just a very quick recap. We've talked about this next generation theorem, which is about decomposing a matrix. This is done in a very general sense here, but what we're actually going to be doing is we're going to be decomposing this mutant Jacobian, okay? And we're doing this because we want to translate from one typically harder eigenvalue problem to an easier eigenvalue problem, okay? That's essentially all we're trying to do here. So let's apply this to our structure competition model. In fact, I'll just go all the way back up a second. You remember the mutant dynamics for our structured competition model were given here. So we've got young individuals, we've got adult individuals. We can write down a Jacobian for those invasion dynamics. Now let's decompose this Jacobian in a sensible way. In fact, I'm going to copy the Jacobian down here just so we've got it handy again. So we're taking this Jacobian matrix that we found earlier, and we're going to be decomposing this matrix to find its next generation matrix, okay? So this next generation matrix is telling us about what is the contribution of each of these different mutant classes to the next generation or the growth of this mutant population, okay? So the first stage we have to do is we need to do this decomposition. So we need to choose matrices F and B, and we need to do them in a sensible way that satisfies these criteria, okay? So let's choose our matrix F first. So F is going to be a matrix such that all elements in F are non-negative. What I mean by F being greater than or equal to 0. All elements within F are non-negative. Now, one of the reasons this is used in biological contexts very often is because when you make certain biological not assumptions, when you choose these matrices in a biologically meaningful way, these conditions up here, 1, 2, and 3, are automatically satisfied. We're going to check that they're satisfied, and we need to think about what exactly it means, because there are many different ways in which one could make this decomposition, okay? Well, let's choose a biologically meaningful decomposition, and then those criteria are automatically satisfied. It also means that your next generation matrix tells you something meaningful as well. Okay, so what we're going to do is we're going to say, it should be F, I, J. We're going to say that this matrix F is just going to contain all terms from our mutant Jacobian that correspond to reproduction for our mutant phenotype. In other words, I mean, this is birth of new individuals, or if this was an infectious disease, it would be transmission, so new infections, new mutants that are arising. And when I say new mutants that are arising, I'm talking about reproduction of those mutants, not mutations. Okay, so we've already had our mutation. Now I'm going to see, is that mutation going to spread? Is it going to grow? So F is just going to contain terms that correspond to births. So F sub ij, the ijth element of this matrix F, is going to give us the rate at which new individuals appear in class J per individual in class I. So for our matrix above, we can just write this down as F is going to equal, well, let's go through each of the elements in J mut. This entry here corresponds to deaths and deaths of young individuals and maturation of young individuals. So no new individuals are produced here. Okay, they're just dying, or they are, yes.
So isn't the death of adult individuals?
It's death of, no, we've got it in both of the equations. Yep. Okay, so we've got deaths. In this particular case, it's death of, with respect to our young individuals. It's maturation of those young individuals. No new individuals are being produced. So because of that, this first entry of F is going to be equal to 0. Okay, remember we're defining these entries. Either ijth element of this matrix F is the rate at which new individuals appear in class J per individual in class I, according to our Jacobian. Okay, so no new individuals are produced here. The next entry is going to be exactly this entry here. So that term is going to be R times by 1 minus AMR A star over KM. Okay, so these are births, so new young individuals that are produced by adults, adult mutants. A word of caution here, this is not what our model shows, but I'm just going to demonstrate something quickly. Suppose there was some additional term in here. Suppose I'm just going to say, for example, this was minus D, I use a different term. Let's go minus C times by, actually, it doesn't even need to be anything. That could be minus C. Suppose there's just some additional term in here that corresponds, say, to deaths or to movement to different classes or whatever. I only take the terms from this matrix JMUT that correspond to births. I don't take the whole element. So you can think of this is the ijth element of JMUT, but that might encapsulate many different biological processes. I only want, for my F matrix, the births. So I just take that birth term out. Okay, so it's important to distinguish between the elements of a matrix and the terms within those elements. Okay, yes.
But like we're doing the 1 minus thing, right? For the competition with the AMR term.
Yes.
Shouldn't we put that in the other matrix?
I will come back to that in just a second, but yes, that's a very good question and a very good point, and I will, yeah, I'll come back in just a second. But well spotted. Okay, so that little demonstration now, I'm just going to erase that. I just wanted to make sure it's clear that we're talking about terms rather than elements. Okay. So Daniel raised a very good point here about this competition term. Now, this competition term here, how I've set it up in our original equations, if we go all the way back to the start for our structured model here, this term here, I'm defining to be our births, okay? So we can interpret this biologically as being some intrinsic growth rate based on the density of adults of this particular phenotype. However, you can think of this term then, this brackets, as being competition for resources. So if there's not many resources around, they can't reproduce. Okay, so this is not deaths of individuals now. This is all about births. Okay, deaths are dealt with in these death terms here. Okay, so there's no density dependent death rate now. This is all competition that affects reproduction, which is why it's going in this reproduction term down here. And this links nicely into what I was going to say next. So thank you, Daniel. Which is this. Sorry, I'll carry on with my next stage. The bottom two terms are going to be 0 based on the arguments that we had before. Okay. Maturation is not new individuals and deaths is not new individuals. So those terms become zeros. Yes, Oliver.
I might have like this might be like a little bit of a silly question.
No, please.
Is there a difference in treating the user like less birth rate rather than more death rate? Because the general population dynamic is the same, right?
There is when you come into doing things stochastically sometimes.
Yeah.
As far as this is concerned, it depends a little bit on this interpretation of F being greater than or equal to 0, because here, like, you can decompose that matrix in that way as well. We tend to decompose this as like, this is the birth term, so we are only going to focus on this when this is non-negative. So this links into this part here. So if it was deaths, then this could be negative and could be larger than R. However, because we're treating this as a birth term, we're basically saying that this is true provided our, let's highlight it, provided AR star, or I've got it as just A star here, times by the competition strength AMR is less than KM, K of XM. This is.
And you're saying stochastically it changes because
In some, yeah, when you do stochastic models, sometimes whether you like, yeah, it can change in stochastic models how you interpret, how you go from a deterministic, let's say, logistic growth model, whether you treat things as being birth terms or whether you treat them as being death terms interaction. So that can sometimes matter there, but But what we're going to do here, we're basically restricting ourselves to the case where this is always non-negative. Yes, Mark?
How come the bottom left term isn't G? So would we not say that like the growing into the adult stage would be adding to the adult stage would be like extra?
Because we've not added any new individuals to the population. So you've taken one from the juvenile class and you've added one to the adult class, so the net effect is 0. Yes.
So is the reason that other entries are all 0 because G and D are talking about that rates and maturation and they don't actually tell you words?
Exactly. So we only in this matrix, we only want terms from this matrix, J mut, that correspond to births. And the second part down here about F being greater than or equal to 0, we are necessarily restricting ourselves to values of A star where this is well, it is necessarily restricted there anyway, because otherwise, like A star can't be greater than KM over AMR, because otherwise it would be negative. And then the other terms would also be negative, so we couldn't be at an equilibrium. So this necessarily at the equilibrium is always going to be non-negative. Okay, so yeah, so that kind of hopefully answers 2 questions there. One is to why these 0? Well, because there are no new individuals produced, and then this here is non-negative because our A star has to be less than KM over AMR for us to be at that equilibrium. Okay, so the key point here, though, just to take a slight step back, is that we just want to take those birth terms from here, and if we choose birth terms, because they're births, they can't be negative, right? We can't have negative births. So that's why choosing a term that corresponds to birth and restricting yourself to a domain that makes sense for this to be a birth term means that this matrix then is always going to be greater than or equal to 0. All elements are non-negative. So that's the first matrix. And actually, that's the only matrix that we need to kind of make a choice about. Because our decomposition that we had up here, A is equal to F minus V, this is now going to be J mut is going to be equal to F minus V. That means that our V matrix is just going to be this matrix minus our Jacobian. Okay. So what does that look like? Well, this is going to be D plus G, 0, minus G, and D. So we take that matrix that we've just defined F, we subtract our Jacobian. This J is going to be our J mut. Say. And again, this also has meaning. This matrix corresponds to all transitions or movements of individuals from one compartment or class in our model to another, or loss. Okay, so if we examine the terms here, we've got transition from young to adult stages. That's this plus G and minus G. Notice that these transitions are always going to cancel out when you sum these terms together across the matrix. Okay. And then we've got death of individuals, these D terms. So this B matrix is always going to be containing transitions and loss of individuals, which in a biological context is going to be, in this case, death. It could be, in a more general model, it could be something like migration out of a population, and they just kind of leave a population, we don't care about them anymore. So that's why it's called loss, rather than always necessarily being death. Okay. So because this is always transitions and loss, and there's no production of new individuals, remember all the production of new individuals is coming in this F matrix. This means that, sorry, the notation's gone a little bit funny here. If we looked at a dynamical system of some population vector y, if we take the derivative of that, and this is given by minus v times by y, this is just some other dynamical system, this would always tend towards 0 because we've got transitions between classes and loss. This is true as long as there is loss. If you only have transitions and no loss, then this wouldn't be true. So it's kind of like a caveat here, assuming there is some loss. That's kind of more of an aside. we write down what this minus V is. It's just going to be minus D minus G, 0, G and minus D. And we can see from here that the spectral bound of this matrix minus V is going to be negative. In other words, what is the maximum real part for these the eigenvalues of this matrix minus V? Well, we can see straight away here that the elements on the main diagonal are going to be the eigenvalues. D and G are both positive, so these are both going to be negative. So our spectral bound for this matrix minus V is going to be negative as well. Why do I care about that? Well, we go back up to here. We've already seen that choosing births for the birth terms for our F matrix means that it is necessarily non-negative. But this second condition now we've also checked as well. If we have all of the birth terms in our F matrix, then we can only ever have loss or transitions for our V matrix. Okay. The final criteria that we need to check is that our inverse of V has elements that are all non-negative. So we need to find the inverse of a 2x2 matrix. So first of all, what is the determinant of V? We can work out the determinant of V is pretty simple. It's just going to be D times by D plus G. So it's just the product of the elements on the main diagonal of this matrix here. And then our V inverse is going to be 1 over the determinant. So 1 over D times by D plus G. Everyone remember how to find the inverse of a 2x2 matrix, I hope. Ranking out what you learned 3 years ago. Okay, so we're doing it for this matrix V up here, not the second one down here, minus V, remember. So we need to change the order of the elements. Switch, this entry goes down here, and this entry goes up here. So the elements in the main diagonal get switched. We get a D and a D plus G now on the main diagonal. And then the elements on the off diagonal, we just take minus those elements. Okay, so we had a minus G before, this goes to G. We had a 0 before, this goes to 0. We can leave it like that, or we can multiply it out to be 1 over D plus G, 0, G over D times by D plus G, and 1 over D. So clearly, all of these terms here are going to be non-negative. So our matrix, the inverse, has elements that are all non-negative, as is required in our third condition. We'll just go up here. This third condition for our next generation theorem is satisfied. Yes.
Well, we have to know how to find the inverse of 3x3 matrix.
No, I'm not that evil. I'm somewhat evil. I'm not that evil. Fair enough to check. I will expect you to know how to do a 2x2 matrix, okay? Like 3x3 is just laborious. 2x2 is fairly straightforward to do, so I'm not going to ask anything more than that. I haven't written the fourth homework assignment. If I was to put it on the fourth homework assignment, then I would you can use software to do it, basically, if it was to do it. Okay, so we've got all of the ingredients we need to do our next generation matrix. So we now just need to calculate F times by V inverse. So our F matrix, if you recall, was 0, and then our birth term R times by 1 minus AMR A star over KM 0, 0, and then we've just found this V inverse here. A little bit of matrix multiplication. The nice thing now, if you notice, is that we're going to have lots of terms are going to be going to 0. So this top left entry, for example, is just going to be RG over D times by D plus G times by 1 minus AMR A star over Km. In the top right-hand corner, we're going to have 0 times by 0. And the top right element times by 1 over d. So now we're going to have r over d times by 1 minus AMR A star over Km. And then because we've got these zeros on the bottom of our F matrix, these bottom two entries are going to be 0. Yeah, just note that this is an example. You will not always get the same exact structure as this. But one of the nice things is that in many, many biologically realistic scenarios, when you choose your F and G according to the rules that I've described, we end up with this next generation matrix here. Why is that nice? Well, it's nice because this is not only in upper triangular form, but this eigenvalue here in this case is 0. So I know that my leading eigenvalue, our invasion fitness, which is the whole reason we're doing this, is going to be sign equivalent to this minus 1. So I've not had to solve a characteristic polynomial. I can just read it straight on. Like I say, you can't always guarantee this. You might have cases where the next generation matrix doesn't make things simpler. But in many, many cases it does, which is why it's so useful. Yes.
Sorry, you said that this is just like an example of something we could get, or wouldn't this really just be fairly similar to any example we have, except for the fact that our constants would just be a bit different?
No, because there are examples where you might get this entry here being non-zero. We could have scenarios where, say, you could have scenarios where every class contributes something to reproduction. Here, say we've only got the adults contributing to reproduction, in which case you would have entries in more of these.
Right.
So it doesn't necessarily, and also this is just one example of juveniles and adults. There's various cases, from infectious diseases or movement between patches and things like that that might give you different structures. So that's why I say can't guarantee that it will always be like simplify the problem, but in a lot of contexts it does. Okay. So we can just now write down our, so it's clear that our spectral radius is going to be given by this element in the top left of our next generation matrix. So we can therefore conclude that our invasion fitness is sign equivalent to, I'll call it W tilde. In this case, it's going to be W tilde of XM XR, so just like our normal invasion fitness. Sign equivalent to this top left entry minus 1. This minus 1 is because we just go all the way back up here for a moment. We've shifted the problem from the boundary where we care about being at 0 for our spectral bound to our spectral radius, the boundary is at 1. Okay, so if we just subtract 1 here, then the right-hand side is going to go to 0. Okay, so that's why we can say it's sign equivalent to our invasion fitness is going to be sign equivalent to this fitness proxy. So I call it a fitness proxy because it's not actually your invasion fitness. We've transformed the problem, but it has the same sign. And that's the thing that we care about. So we can write this, for example, for our model as just some constant C as by, well, if we expand out our competition coefficient here and our, so we've got our competition coefficient AMR and we've got our carrying capacity KM. We did this previously in an example, so I won't go through all the algebra here, but we just multiply out all these exponentials, and we end up, in this case, with e to the xr minus xm plus xm squared times by a star. This step here is just substituting in what I define AMR and KM to be right at the beginning of the lecture. This stage, kind of don't worry about it too much. This is just substituting things into this equation here. I don't want to spend ages kind of going through the algebra of doing that. You can work through that stage in your own time if you so wish. And I just, this C here, I've just collapsed all of these terms into one new parameter C, okay? And sorry, this should have a -1 on the outside. Like I say, although we've shifted from one eigenvalue problem to another, we still got to find eigenvalues. This biologically realistic decomposition of a mutant Jacobian usually makes finding this proxy, so this is my fitness proxy here, W tilde, much simpler. And like I said, this is even more powerful when J-mut is larger than 2 by 2 matrix. It's not terrible to find eigenvalues for a 2 by 2. It is a problem typically if we're going to 3 by 3 or 4 by 4. Instantly, you did ask me if you should know how to find the determinant of a 3 by 3 or eigenvalues of a 3 by 3. No, you didn't ask about 4 by 4s. You won't be. Okay, we're about 20 minutes left. So that's the gist of the next generation method. The kind of key points are about it. Like that's the new material in a sense for today, right? How do we apply this method? Just for the sake of kind of completeness, I'm going to sort of step through how, you know, the standard adaptive dynamics routine, just to kind of drill this into you guys. So remember that we start off, you know, we need to find our ecological dynamics. We then find our invasion fitness. We've essentially, that invasion fitness is this whole next generation step. We still need to do the rest of our adaptive dynamics analysis. So we still need to calculate our selection gradient, find any singular strategies, and then determine evolutionary convergence stability of those singular strategies. So I'm just going to show you I'm going to go through the working of these. I'm going to write down the answers here. And I'm going to leave it as an exercise for you guys to practice, because I know you guys are often crying out for examples to practice. I'll essentially provide the steps along the way. You should probably go through in your own time to make sure that you can go from this fitness proxy here to the same points. Also, just to sort of note, although this isn't the actual invasion fitness, because it's sign equivalent to our actual invasion fitness, and we only care about the sign, then it's going to have the same sign as the selection gradient. It's going to have the same singular strategies. It's just, you can think of it as being something like this. I'll do a little sketch here. If my invasion fitness, my actual invasion fitness looks something like this, maybe I've translated it to my fitness proxy that looks something like this. The key point is they have the same sign. The selection gradient is going to have the same sign. They're going to have the same singular strategies. Evolutionary stability, convergent stability, they're all going to be the same thing. Okay, so the rest of the process, even though we're now working with a fitness proxy rather than actual invasion fitness, is identical to if you're doing the actual invasion fitness. So it doesn't matter as far as adaptive dynamics goes. Okay, so what are our selection gradient? So our selection gradient in this model, we call this S tilde. Typically going forwards, I won't distinguish with tildes what is a fitness proxy, in future lectures. I'm including the tildes here just to emphasize that it's a fitness proxy. Okay. So we take our partial derivative of our invasion fitness proxy with respect to our mutant trait xm. And evaluate this xm is equal to xr. We've got our invasion fitness up here. I'm taking my derivative with respect to xm, which appears here and here. If I do that, I end up with CA star times by 1 minus 2xr. The reason being is that when I set, we'll still have an exponential term when we take the partial with respect to xm, but then when I set xm equals to xr, we're going to end up with e to the 0, so that just goes to 1. Okay, so our selection gradient looks a little bit nicer. From this, it should be pretty clear as well that a singular strategy x star being equal to 0 occurs if and only if x star is equal to a half. So A star is our non-trivial equilibrium for our adults. That can't be negative or 0. C is just a combination of our parameters in our model, so that can't be 0 either. So 1 minus 2 x star must equal 0, so x star must equal a half for our singular strategies. Okay. Okay. The next thing we do is work out our evolutionary stability. It can be shown, again, this is an exercise. When you do this, you should end up with minus brackets g times by r minus d squared. You might recognize this from earlier in the class. This was a condition I had all the way back up. For those that have good memories here. Essentially, when my resonance equilibrium is biologically realistic, we found that it was locally asymptotically stable. And this is the condition for it to be biologically realistic as well. This condition, therefore, we note that it appears all the way down in my evolutionary stability here. So this term must be positive in the brackets, therefore E must always be negative. So the singular strategy is always evolutionarily stable. We can also see if you calculate the cross derivative of your invasion fitness proxy, so with respect to xm and with respect to xr, and evaluate this at the singular strategy. This cross derivative happens to be 0. This keeps happening in these models. It's due to the particular functions and structure of this model. Just note that this is not true in general, okay? So although this keeps happening, it's kind of happening because the choices of the model are, the model choices that we're making are sort of designed to kind of simplify things nicely. This doesn't always happen, okay? So this cross derivative is equal to 0. So if you remember our criteria for convergent stability is then going to be this cross derivative, which is 0 plus our evolutionary stability back into E. E is less than 0, so C is less than 0. And therefore, we can show that this X star is both convergent stable and evolutionarily stable. Okay. Like I said, that is essentially a whistle-stop tour through the rest of the adaptive dynamics process. I've not gone through that in a lot of detail because essentially I kind of wanted to leave that one as practice for you guys. The main thing I wanted to focus on today is how do we derive that invasion fitness proxy in the first place. So this comes back to your question earlier, Javad. So this all comes down to this sensible decomposition, right, of our mutant Jacobian. By splitting this F matrix to only contain the birth terms, remember birth terms, not elements, of our mutant Jacobian. And what this next generation matrix is basically saying is that ijth element is the expected lifetime number of type I individuals that are produced by type J individual. So let's go back up to our next generation matrix up here. So this is saying my type I individuals here are my young mutants. How many young mutants are produced over the course of a lifetime by individuals that are currently in that young class? Well, essentially this term here is telling me something about, well, the R times by the term in the brackets is how much they're going to reproduce when they're an adult. And the G over D times by D plus G is telling me essentially how likely are they to become adults, and how long do they live as an adult when they're an adult? So there's a biological interpretation to these terms when we translate it into this next generation matrix. It's telling me, okay, well, young individuals don't directly produce new young individuals. They have to mature first, and that's going to depend on their maturation and death rates. And then once they get there, then they're producing them based on this rate, this R times by 1 minus AMR A star over KM. This term here is saying, okay, what is the lifetime, given that someone is an adult, what is the lifetime production of young individuals from adults? Well, it's going to depend on the birth rate. It's R times by the time in parentheses, multiplied by 1 over D. 1 over D is going to be the expected time that they spend as an adult, because they die at rate D. So again, there's a biological interpretation that we get from this matrix that we don't get from our J-mut matrix. So we were discussing in the break, there are other reasons as well that one might want to make this translation, even if it doesn't make the eigenvalue problem easier, even though typically it does. It gives you some extra information that you wouldn't have had previously. Yes.
So these biological like interpretations we're getting by looking at this, these would vary though, depending on.
Yes, exactly. This is just for this particular example, but yeah, you can often then break it down to try and understand, well, okay, given that the ij component is the production of lifetime production of type I individuals from J individuals, well, that's kind of how it feeds in. Yeah. We can see here these terms 0 then come about because this is saying type I individuals. So this is young individuals that produce adults. Well, they're already captured elsewhere in the matrix, basically. Young individuals only produce adults by maturation. So that's kind of captured in these terms here. And likewise, adults only produce adults through these processes of birth. Right. That's a little bit more abstract. Understanding the first row is a little bit easier. Okay, so let's see. The other way of thinking of this is a generational output. So again, that's where the next generation comes from, is like over the course of a generation, how much are you producing for these different classes? The other way of looking at this is this row, the spectral radius row of our next generation matrix is the expected lifetime reproductive output of an individual that is born. Okay, so given an individual is born, just go back up to this here, a new mutant that is born, because this is going to be their fitness proxy -1. This tells us how many individuals we expect that mutant to produce over the course of their lifetime. Incidentally, this has its ground, this next generation matrix has its ground in epidemiology. And for those who are familiar, especially looking at you, Javad, maybe, this is your R0, right? It's your basic reproduction number in an epidemiological model. If this R0 is greater than 1, disease can spread. If R0 is less than 1, it can't spread. So it's basically the same process, but now applied from epidemiology to evolution. That was more of an aside for people who are familiar with those. Okay, I'm going to stick around for the next 10 minutes. I've left here an exercise in case you guys want to practice it, so you can familiarize yourself with the next generation matrix. I'd say just try and find a proxy for the invasion fitness. Don't worry about the rest of the analysis unless you really want to do that. If you want to leave, that is also fine. If not, I will hang around for 10 minutes and you can ask me questions about the method. But yeah. Okay. You can assume, for the purposes of this, that the non-trivial equilibrium exists and is locally asymptotically stable. Again, you might want to check that in your own time, but for the purposes of here, I just want you to focus on finding the next generation matrix. Your A star is equal to 1 over A log of B over P. Okay.